So here I am on a Friday night, and I just had this raging question that I needed answered, and I figured we could, walk it through together. And this question goes something like this. So we have two spherical tanks that are open to the atmosphere. And in these tanks, they have some height of water in them, so H1, H2. They each have some radius, R2 and R1. They're connected by some tube that has an area, and tank 2 has a tube of an equal area leaving it. I'm just going to name these tanks tank 1 and tank 2. And both of them also have some flow coming into them. So flow in 1 going into tank 1, and flow in 2 coming into tank 2. So the question is, if we're given our radius, our initial heights, and the area of these tubes, can we solve for the initial flow rate coming into each tank? Let's figure it out. Let's see if we can do it. So if we want to just look at the change in volume of each tank, so our change in volume tank 1 over time is going to be equal to the flow coming in minus the flow coming out. So Q in 1 minus the flow going from tank 1 to 2, so Q1, 2. So that will be how we can calculate our change in volume for tank 1, and similarly for tank 2, we can calculate it with our flow coming in, so Q n 2, plus our flow coming from tank 1, Q1, 2, minus the flow leaving tank 2, Q2. There. So, those are our equations to find our change in volume. And as I said, we're looking for the initial steady state so we can solve for our initial flows coming in. So if we're at a steady state, we know that our changes in volume are going to be equal to 0. So there, now we can just rearrange our equation, and we can get that Q in 1 is going to be equal to Q1, 2. And similarly again, Q in 2 is going to be equal to Q1, 2 minus Q2. Hold on. Now, these are flipped, right? Yeah, Q2 minus Q1, 2. All right, so that is how we could solve for our initial flow rates. So now we just need to figure out our flow rate between 1 and 2 and our flow rate that's leaving 2. And we know that flow rate is going to be equal to the cross-sectional area times the velocity. So we know the areas of these tubes. So we need to find the velocities at these 2 points. So to do this, let's look at just tank 1 here and pick some point up here. And using 2 points, we're going to use Bernoulli's equation, so our change in our energies, so P over rho plus GH plus is going to be equal to 0 because we're at a steady state, so we have no change in energy at these points. So we get P2 minus P1 over rho plus G H2 minus H1 plus V2 squared minus V1 squared over 2 are going to equal 0. There, so now we just need to solve for V2. So we're taking, this is 0.1 and this is going to be 0.2. So this will be V2. So let's look at the pressures. Well, they're both open to the atmosphere because this one's is open this way and this one's going to be open from that tank. So our pressures are going to be equal, so thus they'll be 0, and that becomes 0. Our change in height will stay like that, and then our V1, how can we find the velocity of this point? Well, since the cross-sectional area where this point is so much bigger than this one, we can just assume the velocity is 0. So that makes it easy. We can just quickly rearrange it and solve for V2 is going to equal the square root of 2g times our change in height. H's might not have been the best use for that because I'm looking at just change in height. I'm not looking at the difference between these two, but we will get to that. So if we want to look at the velocity at this point, our change in height will be from going from tank 1 to tank 2. So then it would be H1 and H2, but the only thing is they would be flipped. So H1 minus H2. And then that's our velocity leaving, that's going in the tube from tank 1. So we just multiply that by the area of that tube, then we get that our Q12 is going to equal our area of our tube times our velocity. And there. And we might already be seeing a problem here. So what happens if H2 is bigger than H1? So we can think about it like this. If there's more water in this tank, the water won't be flowing that way. It'll be flowing the opposite. So let's take the absolute value of this and multiply this by the sign that we get from subtracting them. So now we can always get a number under our radical, and if H2 is bigger than H1, then this becomes negative and this becomes negative, so our flow becomes negative. There, so that is Q12, and as we know, Q12 is going to equal Qn1. There, so that is our initial flow rate coming into tank 1. Now what about coming into tank 2? So if we want to solve, we know Q12, so we need to solve for Q2. And we already know velocity, so our change in height is only going to be affected by tank 2. So instead of H1 minus H2, we're just going to be looking at the height of the second tank, so just H2. So then now our Q2 is just going to be equal to the area of the tube times the velocity, 2g H2. And now we don't need to multiply by the sign because we're only looking at the one tank. So now Qn2 will be equal to Q2, so our area of our tube, times the velocity leaving, minus Q12, so the area of the tube times the velocity times our sign we get from subtracting H1 and H2. There, that is how we can solve for our initial flow rates, and then if we just plug in, we know all these numbers, so we can just plug it in and solve it. But let's say that we change, so we know our initial velocities, but then we change it. So coming back here, we know dv1 over dt. So let's say we change our initial or our incoming flow rates. How can we solve for our change in volume? Well, as we know, our volume of our spheres are going to be equal to the cross-sectional area times the height. So we know our heights that it's going to be at, so how can we find our cross-sectional area? So to do that, let's look at a sphere. How can we find, let's take some point on there, R. So we have our height of our water, and it goes up, and R is going to equal the difference between H minus R. That will give us R. And then, once again, we draw lines like that, so we want to find the cross-sectional area of that point right there at some radial position of R. So we know that R is going to be the height of a triangle we form here, and the hypotenuse will be the radius. So little r is the height, big R will be the radius. Well then, just using Pythagorean's theorem, we can find our length here of L. So L is going to equal the square root of the radius squared minus our radial position squared. And then this gives us basically our radius. So imagine we're looking down on it and it's a circle. This L will give us the radius of that cross section of the circle that we're looking for. So, and we know we're looking for our cross sectional area, so we know that will equal pi L squared. So we know L is equal to r squared minus r squared. So we know it's pi times the square root of r squared minus r squared, and all that's squared. So we can just get rid of the square root and the square, the 2, the exponent. So we get pi r squared minus our position r squared. But the problem is we don't know what little r is, but we do know that little r is going to be equal to h minus r. So we can just plug that in, and we get pi times r squared minus h minus r squared. And that's our cross-sectional area at a given height that we can have. So rewriting these, we can rewrite it as our cross-sectional area times our height times our change in height. And our cross-sectional area is equal to pi r squared minus h minus r squared. Multiply that by the height, and then we want to find it for as we change our height. Same thing There. Now we have all terms that we know. So if we can go in, and the next thing I'm going to do is I'm going to write a code so we can solve for our heights given a change in time. It's going to be fun. So hopefully you can stick with me when I try to do that.